Good morning and good afternoon to everyone. This is Bob Hahn and Michael Woznicki from Lumecon, and we're excited to have you here for LED 101. Just real quickly, some housekeeping items. If you have a question, there's a Q&A button that you can hit and you can list your question. We'll try to answer it as we go along, but if not, we'll get to it at the end. There's also a chat button as well. The chat's just for saying hi to your friends or in general, maybe it's a general comment. And so with no further ado, we're going to get rolling. I first would like to introduce our two special guest speakers today. They are from Samsung, and first one, Alex Christensen. Alex is a regional sales field application engineer at Samsung. He's in charge of general lighting and automotive applications. Alex has over 14 years experience in lighting, including 12 years of product design and engineering, both in electrical and mechanical aspects, and has previously worked for many of today's industry leaders. He joined Samsung in 2018, and he has since been helping manufacturers stay ahead of the competition by using the latest LED technologies available in the market. Also joining us today is Corey Pelland. Corey is a senior regional sales manager at Samsung, and he is responsible for general lighting and automotive markets in the Midwest. Corey has 12 years experience in solid state lighting, and prior to joining Samsung in 2018, he held management positions at Sharp, Cree, and ERP Power. So we've got some really highly educated individuals with us today, especially in the LED space, and we're excited to get moving along. So at this time, with no further ado, I take it Alex and Corey, you're on, correct?
Yes, we are.
Yes, sir.
Good deal. Well, we're going to go ahead and get started, and just let me know when you want me to change the slide.
Sounds good. Hi, everybody. This is Alexander Christian. Today we're going to talk a little bit about and kind of give you a small introduction on LEDs, on how they work. And we're going to go into details on some important terms. You go to the next slide. As it was mentioned, both Corey and I, we work at Samsung in the LED division. And we get to see the latest technologies in LED developments, and we're going to bring some of this information to you. Next slide. So today we're going to talk about the construction and basically the theory of operation. We're going to focus on that the most. Then we're going to talk about how white light is actually being produced from an LED. We're going to go over some basic lighting terms, and finally, we're going to talk a little bit about binning and color quality. Next slide. So, what is an LED? An LED is basically a diode. So the diode is one of the simplest kinds of semiconductor devices. Semiconductor is basically a material that can change its ability to conduct electricity. Most semiconductors are made of basically a poor conducting material on which we add impurities through a process that we call doping. When you dope a material, you're adding extra atoms to change the atom balance inside of that material. So in this case, we add free electrons, which would create what we call an N-type material. Or we can remove free electrons, which would create what we call holes, which create a P-type material that's positively charged. So the N-type is negatively charged, the P-type is positively charged. So when you bond an N-type material to a P-type material and you add the electrodes on each end, you pretty much create a diode. So that's the basic construction of a diode. Now, since electrons only travel from a negatively charged area to a positively charged area, the diode only allows current to flow in just one specific direction. when there's no voltage applied to the diode, so when it's just sitting there, electrons from the N-type material basically fill the holes into the P-type material along the junction, which is the part between exactly where they meet. And they form what's called a depletion zone. In a depletion zone, the semiconductor material is basically returned to its original insulating state. Hence why when all the holes are filled, there's no free electrons or empty spaces for them to flow. So the electricity doesn't actually flow. Now to make this diode conduct electricity, we connect the N side to a negative terminal and the P side to a positive terminal. So when the voltage difference between the electrons is high enough, electrons in the depletion zone are moved out of their holes and begin moving freely again. The depletion zone disappears and current travels through the diode pretty much. Now, if you try to run a current the other way, the current will not flow because the holes and the electrons are trying to move in the wrong direction. So the depletion zone just increases. You're making the separation bigger between the two substrates. Now, as a side effect, which is exactly what we're looking for, when the electrons move, the diode itself generates blue light, or in other words, it emits photons. So what you see here on the left side, that is the symbol for a light emitting diode, and as we're talking about electrical power being pushed through this diode. Nowadays, roughly about 60% of that power gets converted into light or lumens, while 40% of it is still conducted into heat. So that heat has to be managed somehow and removed out of this diode. Next slide. Now we mentioned blue light. So when you first when you power this diode on, blue light is usually what is emitted. To create white light, you basically need to mix red, green, and blue light, which will result into white light. So in this case, what we do is, on top of this blue chip, we deposit a mixture of phosphor. When the phosphor has the blue light traveling through it, the phosphor gets excited and starts emitting yellow light, which is a combination of red and green. So now that you have this yellow light combined with the blue light, which still passes through to a certain amount, you get white light. So that's how you create white light. It's just a combination of three colors. Now on the top right, we're showing here what we call the spectrum. So the spectrum of an LED, in this case, you can see the blue between 400 and 500 nanometers. And then as you move closer towards the end, now you're going to see your greens, your yellows, your reds. So this is the amount of each color that's being emitted out of this diode. So as you combine those colors together, the resulting light is white. So the more blue you have, you get closer to one of the more cool white types of LEDs. And as you put less blue and more of the other colors, then you get more towards a warmer color of LED. Next slide. So what you see here is a zoomed in version of an LED. At the bottom, it's called a lead frame, where everything is sitting on, which is basically your metal. It's like a metal frame. Now on this lead frame, now we have to connect this lead frame to an anode or a cathode. So basically the N side and the P side of the diode, which we do using those bond wires. And electricity basically travels through those bond wires to the chip itself, which is just that big chip you see there in the middle. That would be the LED diode, what creates that blue light. So this is what's present below the phosphor. So this shows a picture where we remove that phosphor so you can see it. The other thing that you can see on here is a Zener diode. So the Zener diode is basically a protection device. It's a small little diode that's able to absorb any kind of electrical shock. So it kind of sacrifices itself instead of letting that shock go to the LED die itself. Okay, next slide. So a couple things that we have to be on the same page here are these basic definitions. So when we talk lighting, these are usually what we're talking about. So the first one here is lumens, which is the unit of luminous flux in the international system of units that is equal to the amount of light given out through a solid angle by a source of 1 candela intensity radiating equally in all directions. So that's a mouthful there. So what that basically means, a good example would be the sun here, how the sun basically, or the amount of light that's coming out of a sun would, would constitute the amount of lumens coming out of it. The second thing would be a luminous efficacy, and that's usually measured in lumens per watt. And that's a measure of how well a light source converts electrical power into visible light, or the ratio of luminous flux to power measured in lumens per watt in SI. So this is pretty much what we discussed on the very first slide. And you can see here an example. Lumens per watt would be what % of the light of that sun actually hits the earth. So that would be your efficacy, because not every lumen that comes out of the sun hits the earth. So next we have binning. So when these LEDs are made, there's a variation between chips. So binning is a way of sorting these chips so that all the LEDs from one particular bin look the same and have similar light output. And this is very important on a lot of applications. So as just a big explanation here would be pretty much if you see the color spectrum there, you can separate LEDs in different bins as in what, which color it represents. So you would literally picture different bins that contain one specific color of LED. Next thing is the color temperature or CCT, which is a correlated color temperature. It defines the color appearance of a white LED. So CCT is defined using Kelvin, where warm white or warm light is around 2700 K. And as you go towards more neutral colors, you're around 4000 K. And as you go towards cool whites or daylight whites, you're talking about 5000 K and above. And this can be seen very well here on the bottom left. So on the left, you have a warm white color, a neutral white, and a cool white on the right. Finally, we have color rendering index. Color rendering index is a quantitative measure of the ability of a light source to reveal the colors of various objects faithfully in comparison with an ideal or natural light source. Now, what do we mean by this? We're talking about, so a CRI goes on a scale from, well, negative technically, but it goes on a scale, let's say from 0 to 100. 100 is the light that's coming out from the sun on a clear day at noon. So whatever object you put under the sun, it's the true, what you end up seeing is the true color of that specific object. Now LEDs, there are some LEDs that go pretty close to 100, but generally you will see 90, 80, 70 CRI, what's available in the market. And you'll notice as the CRI goes down, the color reproduction or color fidelity that's seen on objects also decreases. So that 70 CRI, that apple, I don't know, actually, I think it looks a little bit more appetizing. All right, let's go to the next slide. So this is what we were talking about in terms of color temperature. It could be anywhere from 1,000 or even below that, all the way to 7,000. And this kind of shows an idea onto how the color changes over these color temperatures. And on the bottom here, we have a quick example of what a warm white would be versus a cool white would be in an application. It's a lot easier seen when it shines on object than when you look directly at the object itself. Let's go to the next slide. So on this slide, this shows what we were talking about binning earlier. So this table is the CIE 1931 chromaticity diagram. So on this diagram, you see a few things here. So those vertical lines with the numbers on them, those are the different color temperatures that you would usually see. And horizontally or kind of diagonally, I guess, you would see the dotted black line. So the dotted black line is the black body curve. So this curve when we're talking about white color, anything that is on this curve is technically that true white for each one of these color temperatures. So if you look at the intersection between that line and any of these, so let's suppose 2700K, so the first one on the right, where that intersects, that's when, right there, exactly. So that would be like the perfect warm white color would land right there. Now, LEDs, because of these bins and the manufacturing process, it's usually a little bit wider of a yield. So basically what gets manufactured, right? So everybody's trying to keep this yield more in check. I know a fun fact about the black body curve, the way this has actually been defined and created is based on heating up a piece of iron to that specific temperature. That's why you have these numbers in Kelvin degrees. So like a 4000 K would be this piece of iron heated up at 4000 degrees Kelvin, and that's the color that you would see this thing glow. All right, let's go to the next slide. So as you saw in the previous slide, those bins are pretty wide, right? And the reason that is because there is this tolerance in color temperature. So at the 2700K, you have a tolerance here of about 145. As you go towards cooler color temperatures, between like at 6500K, for example, you have a tolerance of 510. And the reason this is because when you're on the warmer side of the color temperature, it's easier to see color differences than it is when you're at the 6500K, where it's more cool white. All right, you can go to the next slide. So on this slide, this shows you kind of one of our bins and how it's defined. So on the left side, you see there the sweet spot would be at 2700K, right in the center of the LED. And as you move left or right towards the bin, you're moving closer to 2800 or 2650. Let's go to the next slide. So in terms of binning, when you get one of these bins that is a full bin, you're basically talking about using in a fixture all those bins, any one of those bins, right? So if you use, let's say, something from a G in a corner to a 1 in the opposite corner, you put these fixtures next to each other, and you will see some kind of a color difference. It's not major, but you will see a color difference. Now, to avoid that, most manufacturers, including us, what we do is we actually allow pre-selection of specific bins. Like in this case, on the right, you'll see the quarter bin selection, where we would try to make most of our LEDs come out of those 4 center bins. So if you have an LED that's like in a A or a 7, and you compare the two, the difference between light is not that different. Next slide. So regarding Macadam ellipses, so what you saw, the original bin description with all those tolerances, that's what's called a 7-step Macadam ellipse. So on a 7-step, that's where you have the biggest color differences from one side to the other of one of these ellipses. Now there's smaller ellipses defined, anywhere from 1 through 7. But generally, this picture kind of indicates and shows you how these Macadam ellipses overlap with the bins that we offer. So for example, the outermost one would be a 5-step Macadam, which covers pretty much the entire bin. And as you move towards the center, you can get all the way down to 3-step, 2-step, 1-step, and then it's like the perfect one in the center there. So Macadam ellipses basically indicates how what the delta or the difference between two potential LEDs can be inside of, in terms of color, inside of one of these color spaces. Let's go to the next slide. All right, so in this case, well, like we were showing earlier, these are the typical approaches for binning. So when you look something around 5-6-step Macadam, you would use the entire bin area. If you want something that's a little bit better with a tighter color, then you would look at what's called an M bin, which is just the center 4 LEDs there. And we also have a new type of binning, which is we call a U-kit. which is basically a 3-step, and we actually follow the outline of these ellipses, so the corners don't actually stick out of the ellipse anymore. Next slide. Now, while those are usually good methods to get the LEDs in an accurate color, you know, the more you narrow down these bins, the more expensive LEDs get, because you're not taking all the LEDs that are being produced at a time, right? So for that, we created what's called kits. Now, what kits are pretty much sets of different bins that can be mixed in at time of production. So in this case, if you look at the K kit, you would have like an A. Let me see here. A good example would be. Let's look at the G kit. That's a very good example there. So the fourth one, the G kit. So in this case, you can see the colors, how they match. So you would get a bin of like a G and a 1. So if you take those two LEDs and you put them next to each other in the same board, once you illuminate these, the color basically becomes average of the two. So you end up your resulting color somewhere in the center of this. So this gives you effectively like a 3-step distribution. So it's hard to differentiate the color between two fixtures. And if you want to go a step even further, we have what's called an N kit, which is a combination of just 4 different kits, bins inside of the center there. So you would put together an A and a 7 or a B and a 6, and that's going to give you something even closer to the center of this color here. So, so yeah, there's a lot of ways to play around with these LEDs and make your color exactly as you want it. And I think that's about it. So unless there's questions, this time I'm going to pass it back to you and take it from there.
Appreciate it, Alex. Thank you very much.
Welcome.
We did have a couple questions, so let's get those out of the way before we continue on. Chris Haig states, what aspect of sunlight is used to benchmark CRI, i.e. color spectrum?
What aspect of sunlight? So it's not necessarily sunlight. It's actually based on an incandescent light source, which is light emitted through heating up of a specific element. Like in a light bulb, you're talking about heating up tungsten. And things that are done through that process, the CRI that comes resulting out of one of those processes is the benchmark for 100. Now, the sun is also 100 because it's similar. It's created through the process of burning. So I'm not sure if that answers your question.
Then the next question is, Michael, this one might be for you. As an industry, do you see less use of CRI and more use of TM30?
That is a really good question. The IES has done a lot of work as far as bringing forth the TM30, which is a more robust aspect of looking at how objects are represented towards true color. But it is also, as a document, is more complicated. And while the IES has done a lot of effort to making it more streamlined, simply put, CRI with a number such as 70 or 80 is really user-friendly, if you will. And so it's a balance as we get into recognizing that there is a much better depiction and understanding with TM30. The market has still been kind of slow as an industry to shift from CRI to TM30. I think it's eventually an inevitability that it will become more widespread with adoption, but I'm not surprised that it is taking long where they get into fidelity and at least 4 core aspects with TM30 as opposed to just CRI when you can have a simple number. That's what we've been seeing over the past 2 years since TM30 got adopted as a technical memorandum.
And I can just add from the LED side, we see 98% of the customers ask us about CRI. A few question and want the TM30 data, which we can share, but for the most part, most customers are still talking CRI instead of TM30.
Yeah, it's mostly something that's geared, seems to be people that are doing more architectural applications is what are asking for that data more. For normal applications, usually CRI because of the simplicity of it.
Thanks, guys. This probably is for Corey and Alex too. As we continue to improve LED's efficiency, where do you see lumens per watt topping out? And I can speak to that from a fixture manufacturer, but maybe from an LED standpoint. Why don't you guys go ahead?
Sure. So looking at just the LED itself and considering the technology, which is basically phosphor converted blue, the theoretical maximum in the lab can be somewhere around, and again, this depends with color temperature, somewhere between 320 and 400 lumens per watt. Now that's theoretical. A more real life, more accurate number would actually be much lower than that. Would be probably around 240, 250, something around there. And again, that also kind of varies a little bit on color temperature. Around 5,000 to 5,500 K is kind of where the best efficacy of an LED seems to be.
And I think many of you in the industry will remember a few years ago when you were seeing 7 and 10% efficacy improvements every year. That's kind of gone away. And Samsung right now, we do have some LEDs that are pushing about 230 lumens per watt right now, and we lead the industry in that regard. But like Alex said, probably 240, 250 is where we may top out for a packaged LED. And after that, Samsung is working on next generation technology such as quantum dots or red, green, blue LED mixing to white, things like that to take us above that 250 lumen per watt threshold. That's
excellent. And basically, to take it the next look at it then, and when you put the LED into a fixture, it's like having a great set of golf clubs. You can have what they use on the pro tour, but that doesn't make you a pro. And it's usually up to who's swinging the club. So with an LED, you can take the best LED, that the Tiger Woods of LEDs, and put them into a fixture, and you can really burn it out. So for example, we're going to talk here briefly about how to thermally dissipate, and what's the next step is the next portion of this webinar about how to dissipate the heat away from the LED so that that Samsung LED can flourish and be in its element. Like my dad used to say, you can put a Ferrari engine on a go-kart, but it's not going to last very long. So we'll get into that real quick. And real quick, Dave Meglio asked a question, will the presentation be available? Yes, we're going to send a recording of it to everyone, or at least a link to that when we're done here today. So the next step, thank you, Alex. Thank you, Corey. Appreciate it. Don't leave us just yet. So in case there's some more questions, we appreciate you hanging around. And I want to get to the next portion, is that when the LED then is manufactured and shipped to what would be a board supply house. So locally, Lumecon, for example, we've always used local suppliers to not only manufacture our LED boards, but then to place the LEDs as well. So basically, to make an LED circuit board, you start off by designing a Gerber file, and that is the outline of the electrical current, electrical circuitry that goes on the board. Then you take a bare piece of aluminum and you coat it with a thin layer of copper. Then you take the design and photo etch it into the copper. And by then pouring a solvent on it, you actually eliminate the copper and leave the design behind in the copper traces. And then you can see why they're white is that usually there's a Kynar solution, type of Kynar solution that's kind of a woven material, if you will, that allows heat to go through it, but also insulates the board against, shorting out the LED. So then you coat the board with that, and then you place the LEDs on them. A good example to show you of this, this is one of our local houses right here in Detroit. And we're going to show you this little film clip. There's actually 2 Samsung pick and place machines sitting right there. And so the LED board itself, this one actually is a little out of order, but I'll show you what happens here in a sec. If you look closely, you can see a wet solder paste being silk screened onto the LED board. The solder goes exactly right onto the pads. And then you can see here that the LEDs then are being picked up from the reels and placed onto the wet solder. So they're floating now on wet solder, and they get pushed down the assembly line, and then they go into a heater or dryer. And so we'll show you a picture of the dryer here. And it's kind of like, you know, if any of you have ever silk screened t-shirts, the method is very similar. So this is a long dryer right here, and it goes from low temperature to high temperature, back to low again, to cure the LEDs to the board. And the last step Lumecon does, and this is different than most other manufacturers, is we spray a 2-part urethane clear coat onto every LED array. And then you'll see a little needle nose coming down here, and this hits the little connection points on the TI connector as well. The objective here is to protect all the LEDs from salt spray, whether it be from the roads up here in the northern regions, we put salt on the roads, or being near the ocean. And also it takes care of other carcinogens like, you know, well, not necessarily carcinogens, but, you know, dirt, dust, grime, things that can break the LED down and cause it to go away. So the next step is when you're placing the LEDs, in order to have them hit their highest lumens per watt, if you will, and then also last as long as you can, there's 2 ways to do it. One is that many of you have seen LED fixtures that have what's called a COB LED inside of it, or a fried egg, as some of us call it in the industry. And they're those big yellow packages you see, and some have 1, 2, 3, or 4 of them in the package. And what you're really looking at is a bunch of the LED diodes are actually all kind of crammed together under one lens. And so when you put LED diodes that close together in that kind of environment, think of it like you're standing in the middle of a room by yourself and the AC is running at 72 degrees. Now that room's meant to hold 50 people. Let's put 150 people in it, so you're standing shoulder to shoulder. Now, it doesn't matter what the AC is set at, you're still going to overheat and get hot and sweat, because the body exchange heat is being exchanged back and forth in such a way that no matter how hard the AC pumps, you're just not going to cool each other off. Same thing happens when you place diodes too close to each other too. They become overheated, and it really limits its lifespan. So at Lumecon, we prescribe to placing 1 LED, 1 diode, and it's called discrete LED placement. And what that allows us to do is gives it a lot more breathing room. And comparing the 2 in the lab, the same amount of lumens, the same array, you're probably going to get run about 20 degrees cooler, which allows us to get 100,000 hours or more out of the same LED that would only be rated for 50,000 hours where they cram together like a COB is. So you're seeing in the industry, a lot of people who went to COBs are now coming back and going to mid powers and others because of this. So then to maximize that LED and allow as many photons to escape as possible in their brightest form, you need to be able to pull the heat away. So earlier, Alex showed the symbol for the LED diode, and that 60% of its energy was going up as in photons, and then 40% was being drawn off in heat. And so the objective is to grab that heat and drag it away from the LED through the bottom. So you can see that this LED is placed on a metal core board and then onto a heat sink. And then in the industry today, many people aren't using heat sinks anymore. Now they're actually attaching the LEDs right to the, you know, the LED boards right to the fixture itself and using the fixture as the heat sink, which then provides a nice flow, a conductivity to allow as much heat to be dragged away from the LED and as many photons to escape out the front, creating as many lumens as we possibly can per watt. And so at Lumecon, we call that our enhanced thermal design. It's our ETD. And whether we're making a retrofit kit or whether we're designing our brand new Detroit series line, we use the same methodology. Don Lincoln, our senior vice president, has very strict standards on how hot an LED can get so that we're able to maintain our warranty. Our warranty is a 10-year warranty to L70. So in the industry, you really cannot, you know, an LED doesn't typically catastrophically fail. So what is its lifespan? And so in the industry, we've kind of drawn the line at a 30% depreciation in light output is probably a good measuring stick of what its lifespan should be. And so at Lumecon, we warranty to L70, meaning that there's still 70% of the life left. So the proof is in the pudding. So this is kind of a neat experiment that we did. So back in April 29th of 2009, we sent out one of our first wall packs and we had it put into a sphere and a goniometer. And the totals are derived, and at 30 some watts, at about 31 watts, we were running at 1,731 lumens. We then took that fixture and we put it on the back wall of our building when we moved in, and we never turned it off. So 10.5 years later, on October 15th, we took it down, we shipped it off to the photometry lab again at CSA, and we had it run again, the same exact fixture. And you can see that we went from 17,000 lumens to 12,000 lumens. And so our lumens per watt went from about 45 lumens per watt down to about 31 lumens per watt, all running at about 40 watts. And so that is a 28% depreciation of lumens over a 10.5-year period, which places us well within our threshold of warranting to L70, meaning that if it drops more than 30% over 10 years, we'll warranty it. So this is a great example here. And as Alex and Corey can attest to, you know, we were using a Cree XRC LED, which just wasn't as efficient as they are today. So for example, when they showed the 60% lumens photons going out and 40% heat, maybe back then it was a little less than that. Maybe it was more like, you know, 20 to 30% photons going up and the rest was often heat. So they've come a long way in technology of LEDs and making them much more efficient. So bringing that all together and kind of wrapping up here, you know, we've gotten to know Corey and Alex throughout the years. And I would love to say that they come to the Detroit area all the time because they love Lumecon, which they do if you ask them. But really, since we're surrounded by all GM, Chrysler, and Ford, in many cases they're here to visit those guys to sell their LEDs. But we do get quite a lot of attention in this area because a lot of the LED headquarters are located right here in the metropolitan Detroit area. And so also using this map just a little bit, using our Detroit series, for example, if you look over here on the west side of the state where I'm circling, this is Muskegon, Michigan, and that's where a lot of die casting occurs, and that's where our Detroit series is being die casted. And then if you come all the way up here, you see Charlevoix, Michigan, and that's where most of our lensing comes from, injection mold prismatic lensing. And so those all make their way down to the Detroit area where we then place our LEDs on our boards, and then we put everything together right here at our Lumecon headquarters. Now, we're in a precarious time. We really are thinking about everybody, and you know, being that we were founded in 2006, we have 14 years under our belt. And, you know, we come into this summer, which is was going to be was to be a real exciting time for us because we were launching our Detroit series this summer, and obviously, you know, the pandemic has been playing a havoc with everyone, and so we're thinking about everyone out there. We want you to know that, you know, Lumecon, we were founded in 2006, but our sister company was founded in 1945. So everything we do is looking at the long run and the long game, as opposed to, you know, just immediate. So we're going to be around for a long time, and we want to be here to help you out. So pulling that all together, you can see what business is out there today. There's still a lot of federal business to be had, even during this time frame. The feds are still purchasing, and a lot of public works are still going on. And so because of our local content, Lumecon really does fit the bill for most Buy American Act oriented projects. So we do meet level 2 and in some cases level 3 of the Buy American Act, and on every product that we manufacture today. So at that point, there is another question. And that is there an app that we can use for lumens measurement? Now, if Corey and Alex, if you want to speak to it, I've seen online calculators before, as far as you know, combining with power factor and everything to see what you might max out on a fixture. Is that correct?
Well, if we're talking strictly lumen measurement, there's a couple of things to note. So when you measure lumens, you have to measure it. The amount of lumens is basically light that goes in a specific area. So it's very hard to measure with a device. A device, what usually measures its lux, or basically the luminous intensity of a specific point. So if you're talking about an app on, let's say, on your phone, there's plenty of apps out there that can give you, based on your sensor on your phone, they can give you the brightness and lux, but that's not going to tell you much. So to measure lumens, you need to use either an integrating sphere or a goniophotometer, which takes all the lux measurements around a fixture and adds those up together to give you a number of lumens. So it's a slightly different measurement, if that makes sense.
Thank you, Alex. Appreciate it.
Welcome.
Here at Lumecon too, when we take the LM80 data from Samsung, and we're able to plug it into a calculator if you're looking for a TM21 calculation. So, you know, basically that's combining the LM79 report with the LM80 report, and then you incorporate the heat rise, the in situ test from the LM79 report, and you're able to derive a projected lifespan of that product with the LED, with the driver, with the surge suppression, with the housing, everything included. So that is something that is available online if you dig hard enough.
And just want to add real quick, one lux is basically 1 lumen per square meter. So if you have an area you want to measure, and you measure the intensity of light over that 1 square meter area, so if you measure, let's say 50 on all 4 corners of that area, then you can safely say that you have 50 lumens emitted to that surface. So I guess that would be one way to measure it with a phone.
Gotcha. One other thing too that we wanted to mention, and that backing up to when Alex was talking about binning, back in the days of 2006, 2007, when we were building light engines for the Army, we would get LEDs in, and we actually had to bin them ourselves, because we were, when you looked at the ellipse, we were definitely getting step 7 ellipse, meaning that we were getting every single variation. And it wasn't until several years later that the LED manufacturers were able to start squeezing down and getting more into the sweet spot. so that we no longer had to bin anymore. But still today, there's a lot of manufacturers that if you find a very inexpensive fixture, one of the reasons why it can be so inexpensive is that they're willing to take a much larger ellipse of bin, so a step 7, let's say, and then LEDs don't necessarily quite match each other, and you're not getting a nice clean array. It's kind of like walking into the grocer and he's got a whole rack of apples, and some are bad, some are okay, and some are ripe and fresh. He's going to give you a better deal if you buy all of them than if you just want the ripe, fresh ones. And at Lumecon, for example, and many other manufacturers, we normally are only buying the ripe apples as opposed to taking the whole bin. So that's kind of an analogy that we like to use, but then that's how you save money in this industry and bring out less expensive fixtures is by lowering the quality of the product. Is there any other questions out there right now? Okay, well, we've thoroughly enjoyed having everybody on here today. For Michael and I, it was a treat to have Alex and Corey on the line with us. Thank you very much, gentlemen. Appreciate it.
Thanks for the opportunity.
Yeah.
Our pleasure.
And we'll see you guys down the road, and maybe you can be on a future webinar with us again. We appreciate it. Thank you, everybody.
Stay well.